Today we are going to see Chebyshev'S inequality. So we know that if X is any distribution with mean mu and variance sigma square, then X bar is an estimate of mu and S squared is an estimate of sigma square. So here Chebyshev's inequality shows that the difference between the estimate and the population value is how far it is closely related. That is, we can find the lower bound or upper bound for the difference of the estimation and the population value. So first we will define what is Chebyshev's inequality. So statement: if X has a distribution with mean mu and variance sigma square, and for any value k greater than 0, we have this probability of modulus of x bar minus mu less than or equal to k sigma is greater than or equal to 1 by k sigma. So this is the statement of Chebyshev's inequality. So it gives the difference between the closeness of x bar and mu. How far it is close to x bar and mu. So that is the objective of Chebyshev's inequality. So here we can say the distribution of x is not known here. We can take any distribution, so that is not at all a problem. Here we consider the proof in discrete case. Okay. So let x be the discrete random variable with Pm of f of x. So let us prove the theorem in discrete case. Let f of x be the Pm of x. Then we know that the definition sigma square equal to expectation of x minus mu whole square. So for a discrete random variable, it is given by summation x belongs to S of x minus mu whole square into f of x. So if it is a continuous case, instead of summation, we'll use integration. That's it. So next we will we have sigma squared is equal to summation x belongs to S of x minus mu whole square into f of x. Now we will divide this into two parts, namely summation x belongs to A of x minus mu whole square into f of x plus summation x belongs to A dash of x minus mu whole square into f of x. So we have divided the summation into two parts. Here A is nothing but the space set of all x such that this modulus of x minus mu greater than or equal to k sigma. So we are defining A like this. So the whole space S is divided into sum of A and sum of B. Now this if you see this equation 1, the second term is a sum of positive quantity. Since it is x minus mu whole square into f of x, this is the sum of non-negative numbers. So obviously it is greater than or equal to 0. So the second term of equation 1 is a non-negative number. Hence, if you remove the second quantity, this equation becomes greater than or equal to. Hence, we have sigma squared is, instead of equal to, we will have greater than or equal to. So, because we are removing this term, we are removing a sum of positive term. So, obviously, the left hand side becomes greater than. So, sigma squared is greater than or equal to sum of x belongs to a of x minus mu whole square into f of x. Okay. Now, in A, in the space A, we have modulus of x minus mu greater than or equal to k sigma. So, this implies x minus mu whole square. Squaring both sides, x minus mu whole square is greater than or equal to k square sigma square. Therefore, we can substitute for x minus mu whole square in equation 2. So, we get so in equation 2, we will substitute for x minus mu whole square. So, we get sigma squared is greater than or equal to sum of x belongs to a of k square sigma square. Instead of x minus mu whole square, we have k square sigma square into f of x. So, k square sigma square is a constant. We can take it outside. K square sigma square summation x belongs to a of f of x. So, we know that by definition or properties of PMF, probability of x belongs to a is nothing but summation x belongs to a of f of x. So, using that, we can write this as k square sigma square into probability of x belongs to E. Okay. Now, in A, we have this probability value is probability of modulus of x minus mu greater than or equal to k sigma. So, in A, we have this one. Okay. So, in the left hand side also we have sigma square. So, bringing this k square sigma square to the left side, we have probability of modulus of x minus mu greater than or equal to k sigma is less than or equal to sigma square by k square sigma square. So, sigma square get cancelled. So, that is equal to 1 by k square. So, we have probability of modulus of x minus mu greater than or equal to k sigma is less than or equal to 1 by k square. Hence that true. So, in the second part, we can reverse this inequality. So, in this way, we can write this. So, probability of modulus of x minus mu less than k sigma is nothing but this is greater than or equal to 1 minus 1 by k square. So, in this way also we can write the probability by reversing this equation. So, obviously these two gives the lower bound and upper bound for the difference of x bar and mu. So, instead of x we have to use x bar. Yes. X bar minus mu, the difference between x bar and mu is very minimal. So, in that way we can see. Next, we have a corollary. Substitute epsilon equal to k sigma. So, in this case, we have probability of modulus of x bar minus mu greater than or equal to k epsilon is less than. So, from this we can write k equal to epsilon by sigma. So, substituting this becomes sigma square by epsilon square. Okay. So, by defining the value of epsilon, we can find the probability. And this equation 3 becomes By substituting epsilon, we have probability of modulus of x bar minus mu less than k sigma, less than epsilon, so less than epsilon is greater or equal to 1 minus sigma square by epsilon square. That's okay. So this can be used in the problem sense. These two equations, correct.